What's going on, Science 10s? It's Mr. Walton here. Happy Tuesday. So today we're going to be working on work. Work has a very specific definition in science and physics in particular. It's not just doing anything. It's not just, being busy and working on stuff. Work is the product. Read into that multiply, right? From a mathematical perspective, when you say the product of two things, you say multiply. So work is the product of a force and displacement. What that means is if I had a box, okay, so a box sitting on the counter or something like that, and Mr. Walton pulls that box to the right. Unless the box is super duper heavy, the box is probably actually going to start moving to the right. And because the box starts moving to the right, because I pulled on it to the right, I'm transferring energy to that box. The box was just sitting there originally, and then I pulled on it and it started moving. So now it's got more energy than it had before. So that is what work is. Work is the transfer of energy, and we'll talk more about that tomorrow. A couple things here. The product of the force and the displacement. The force and the displacement have to be in the same direction. It doesn't make sense that if if this box is, let's say it was moving the other way, right? Mr. Walton's pulling on it this way, but it's actually moving that way. It doesn't make sense that I'm transferring energy to it if it's moving in the opposite direction. Like, that doesn't make any sense. Obviously, I can't be transferring energy to it, okay? So, number one, a couple things. Number one, so the force and the displacement must be in the same direction. Perfect. Number two, loosely speaking, the work is a transfer of energy. So I'm giving energy to the box because it wasn't moving originally, and then because I started pulling on it, it started to move, so I'm transferring some energy to that box. So mathematically, work can be expressed by the following equation. This is on page 5 of your data booklet. So it's force equals, it's work equals the force times the distance or the displacement. Now, we can rearrange this a bunch of different ways, right? We can rearrange it. It's already rearranged or isolated for work. We could rearrange it for force or for distance or displacement if we wanted to. Now, normally, what are these units? Well, work, you don't know what that is. Okay, so let's figure it out. Force, though, that's measured in newtons. Displacement, that's measured in meters. So if we went work equals force, which is a newton, times a meter, because it's displacement, well, that would be our new unit. Work is measured in newton meters, but we call it something else. We call the units for work, we call that a joule. So we say J, or it's the same thing as a newton meter. So those are kind of the two units. There's actually we can break it down more than that into its fundamental units, but we're not going to do that quite yet. We'll do that a little bit later. So let's do a couple examples. Here's our, let's put that in there, joule, perfect. So we're going to be using this equation to be able to solve a couple problems. Hopefully it'll be a pretty short video today, but I've said that before and regretted it. That's okay. So work example number 1. A weightlifter lifts a barbell in a vertical distance of 2.4 meters. If the average force required to lift the barbell is 2 times 10 to the 3 newtons, how much work is done by the weightlifter on the barbell? Squiggly line. So a vertical distance of 2.40 meters. If the average force to lift up, right? So yeah, these are in the same, they're in the same direction, so we're good. If the average force to lift the barbell is 2.0 times 10 to the 3 newtons, how much work, question mark, is done by the weightlifter on the barbell? Perfect. Work is force times distance. We're going to take our force, 2.0 times 10 to the 3 newtons, multiply it by the distance, 2.40 meters. And what are we going to get? Now, we haven't seen scientific notation in a little while. And so remember, I just want to remind you how to put this into your calculator. Give me a second and I'll pull up the calculator that we normally use. There we go. So we've got our calculator that we normally use. And so when we put 2 times 10 to the power 3, remember that the way that we actually do that is we'll go 2, but then we'll go second, comma, because of the EE. Now remember, it's EE, or it could just be E, or it could be EXP, depending on the calculator that you're using, right? So it just stands for scientific notation. 2E is times 10 to the power of, and then we're going to put our exponent, 3. Perfect. 2 times 10 to the power 3. And then multiply that by 2.4, and we're going to get 4,800. So our value is 4,800 and a Newton meter, so Newton meter, or we could say joule. Now we got a little bit of a problem with this. Here, the first value for force, we got 2 significant digits multiplied by 3 significant digits. So our answer needs to have 2 significant digits. So how do we write this as 2 significant digits? We can't just say 48 joules. No, that's not going to work, because it's not 48, it's 4,800. So we're going to have to use scientific notation. We move the decimal 1, 2, 3. It has to be behind or after the first significant digit. So 4.8, and I moved the decimal place 3 times. So 4.8 times 10 to the power 3 joules. That's how much work was done on the barbell. Okay, work example number 2. How much force is required to do 18 joules of work on a 12 kilogram cart over a distance of 3 meters? Squiggly line. So required to do 18 joules of work on a cart that has a mass of 12 kilograms over a distance of 3 meters. Delta D, 3.0 meters. Perfect. And we're going to assume they're in the same direction, because that just makes sense. Here we go. So what does it want? It wants force, question mark. Now, how are work, mass, distance, and force all related? Well, actually, they're not all kind of related to each other. What's going on here is that work is force times distance. So if we want force, we're going to have to divide by distance to be able to get force all by itself, or to isolate for force. So force is work divided by distance. The work is 18 joules. The distance was 3.0 meters. So the force required, 18 divided by 3 is 6 newtons. We are not done yet. What's happening is we've got 2 significant digits on top, 2 significant digits on the bottom, so we need 2 significant digits as our answer. Every answer should have a number with appropriate significant digits and a unit associated with it. Okay. Nice. Okay, less than 10 minutes so far. Pretty good. Let's go on to our last example. So calculate the work done. So, all right, squiggly line, the work done in 7.2 seconds, so that's delta t, 7.2 seconds, to accelerate a 175 kilogram motorcycle, so that's mass, 175 kilograms, from rest to 30 meters per second. What is going on here? From this to that. What does rest mean? Well, that means our initial velocity was 0 meters per second, and our final velocity was 30 meters per second. Strap in. This is going to be a little bit complicated, okay? And we've got a distance of 108 meters. Okay. Now, what's going to happen? In order to calculate work is equal to force times distance. I need both the force and the distance in order to calculate work. Do I have force and distance? Well, I don't have force, but I do have distance. Distance, perfect. Okay, no problem. So all I have to do is calculate the force first, and then I can calculate work. Once I find force, then I can calculate work. Remember that two-step problem that we dealt with yesterday? Okay, so let's go into our data booklet. Now let's see what has force. Well, force is equal to the mass times the acceleration. Perfect. Let's go back here. So I'm going to put another squiggly line. So force is equal to the mass times the acceleration. So this should be easy. Let's calculate force using the mass. Do we have the mass? Yeah, we got mass. No problem. Do we have acceleration? Oh boy. Uh-oh. We do not have acceleration. So unfortunately, we don't have acceleration, so we can't calculate force yet. Oh boy. Let's go back. Let's go back to our data booklet. So force is equal to mass times acceleration. We don't have acceleration, so let's measure acceleration. What do I need? We need VF, VI, and delta t, or the change in velocity over the change in time. Do we have VF? Yes, we have VF. Do we have VI? Yes, we have VI. Do we have delta t? Yes, we have delta t. Good. So VF minus VI over delta t. And we're not talking about this as a vector right now. So we're just assuming it's in like a positive direction. Doesn't really matter. So do we have all of these things? Yeah, we got VF. Yeah, we got VI. Yeah, we got delta t. So we can move forward. This is a 3-step problem. Yesterday we had a 2-step problem. This is a 3-step problem. So the first thing we have to do is we have to calculate acceleration. Then we're going to take that answer and turn it into a force. Then we're going to take our force and turn it into work. That's how we're going to go about doing this, okay? So this is, So this is step 1, this is step 2, and this is step 3. I get we're working backwards. I understand we're working backwards, but just hopefully this shows you the plan of our thought process. So acceleration is VF, so 30 meters per second, minus VI, which is 0 meters per second, divided by delta t, which is 7.2 seconds. So when I do this, 30 minus 0 is just 30, and 30 divided by 7.2 is 4.166666. 16666, blah, 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 meters per second squared. Now, what you have to remember is that we're not done yet. We are not done yet, okay? And our answer, 2 digits divided by 2 digits, should have 2 digits. So just keep that in the back of your mind. But we're not done yet, so we're not going to round. So let's take that information and let's use our mass, which is 175 kilograms, and multiply it by our rate of acceleration, 4.1666 meters per second squared. And that's going to get 729.1666666. So 729.16. And now it's measured in newtons. So we'll take that answer. Again, 3 digits times our 2 digits, right? Our previous answer should have had 2 digits, okay? So we'll take that answer and bring it up here. The force was 729.16 newtons. And we're going to multiply that by a distance of 108 meters, not 180, 108 meters. So we're going to get our work is 78,750 exactly. 78,750 joules exactly, but not exactly, because remember, this answer, I know it doesn't look like it, but this should have had 2 digits, right? Because originally, so we used this answer in here, and then we use that thing in there, right? So 2 digits times 3 digits is 2 digits. So our actual answer should be 7.9 times 1, 2, 3, 4, 10 to the 4 joules. That's the answer, okay? That was tough. I get it. That was really tough. What I want you to do is I want you to do some practice questions. The first kind of 3 or 4 practice questions are pretty darn easy. And then the last one is split up into 2 different sections, okay? So it's split up a lot like this. I'll just show you. So here's practice question number 5 on the next page. It says a 1,500 kilogram car is traveling at 25 meters per second. It takes 50 meters and 8.5 seconds to come to a stop, right? So it's stopping instead of taking off. How much force did it take to stop the car? So the first step, you're going to be calculating force, right? Here, and then you're going to use that answer, whatever your answer is. You're going to use that answer in the next step. Okay, hopefully that kind of makes sense. So I would like you to go ahead and do these questions. Try them out. Let me know if you have any questions. Take a look at the key, like the filled in notes for the answers. As always, I'm available from 10:45 to 11:15 every day in the office hours. Have a good day. Good luck. Have fun.